Hello everyone. In this video, I'm going to talk about fetch unit implementation of y86 sequential processor. Okay. So before we jump into the fetch unit implementation, let's understand encode and decoding of y86 instruction first, because encoding and decoding is really part of fetch and decoding unit. So without knowing that, it's hard to implement and understand what I'm going to talk about. So then what is encode and decode? Basically, encoding is translating the assembly code to the machine code. And decoding is the other way around, like translating machine code to the assembly code. So I know you are learning x86 instruction set architecture in the lecture, and then you will learn how to encode and decode in the lecture as well. But here, let me explain decode, encode and decode with more implementation perspective, okay, using some terminology written in the next slides. Okay. Here we have a figure of 4.2. I take this from the Bryant book, so you can go ahead and read the explanation around this figure. But in this slide, I'm going to talk about important concept. So here we see some familiar instructions like move instructions and jump instructions. But here we have something interesting instruction, OPL instruction, but it is basically set of and actually arithmetic instructions such as add, sub, something like that. But because the arithmetic instructions are all same, have same instruction format, so we just name OPL here. And also with the same reason, all the jump instructions have same format like here. So we use just y86 to represent all the jump instructions. And also we know hold instruction, no operation. Hold instruction stops processor, and then no operation, just do nothing. But here we have more instructions below, but we are not talk about this because we are not going to implement this in this term project. Okay, then let's first take a look at the size of each instruction. The size is important in y86 instruction y86 process implementation because it is variable length instruction architecture. So which means when you see this in one instruction, you see some different size of format, detail breakdowns, okay, like here. So then let's see how many bytes for each instruction. On the top of this figure, you have, sorry, let me draw again. You see the byte information here. So which means we have 1, 2, 3, like byte 0, 1, 2, 3, 4, 5, which means there are 6 bytes in total. And as you can see, the maximum size of this instruction set architecture is actually 6 bytes. Okay, I draw a little bit bigger. So let me redraw this again. Okay, around this. Okay, good. Then we know maximum size of instruction, like biggest instruction is 6 byte long. And then what about these small boxes here? So actually one small box is half of 1 byte. So 4 bits. So as you can see, first box is fit into the first half of the first byte 0. And second box fit into the second 4 bits in the first byte 0. And also in another instruction, like RR move instruction has 2 more boxes, then these 2 boxes fit into the second byte 1. And also another instruction, IR move instruction, for example, has long box here, and this long box fit into the byte 2, 3, 4, and 5. So it takes 4 bytes. Okay, and what else we don't have? Okay, what about jump instruction? So jump instruction has 2 small boxes in the first, and then next is large box. So then I think it is fit into the large box fit into the byte 1, 2, 3, 4, like 1, 2, 3, 4. And then first 2 small boxes fit into the first byte. Then it is 5 bytes in total. Okay, good. Then let's write down the size of each instruction. Like halt instruction has 1 byte, no op 1 byte, R move is 2 byte, and then RI move, like these 3s are 6 bytes, and then this OPL is 2 byte, and then jump instruction is 5 bytes. Okay, then we have 3 cases of instruction size, 1, 2, sorry, 4 cases, 1, 2, 5, and 6, right? So this size information will be used to update PC register value to fetch the next instruction, right? So basically, machine codes are stored in consecutive memory space. So when we fetch a first instruction, the next instruction it will be stored in the next address, right? Then to calculate the next instruction, we can have this equation, like, so current PC will be updated by PC plus length of current instruction, INS, right? So this part is variable, so it can be 1, 2, 5, or 6, right? So for example, if current PC is 0, and then the current instruction is, for example, IR move L instruction, which size is 6, then next instruction will be 0 plus 6, which is 6. Then 6 is the address of the next instruction. So we will implement this part in the fetch unit. Okay. All right. So then we understood the size of y86 instruction. Okay, let me clear this out. Okay. Next, let's understand the meaning of each boxes in the this instruction format. Okay, let me redraw this range again. And okay, so basically, this instruction, all the instruction format has a common information in the first 2 small boxes, like first 2 4 bits or first byte, right? So first box actually fit into the first half in the first byte, and it stores the instruction ID or instruction code to identify the instruction, and it is called I code in the implementation, the diagram we are going to look at the next slide. Okay, so as you can see, each first box in the instruction has different number from 1, 2, 3, all the way up to B, right? Okay, then we can distinguish. When we read first 4 bit, we know which instruction we are fetching. But here we have a situation with these two instructions, OPL jump instruction, because these two instructions actually represents multiple instructions, which means even though we fetch first 4-bit, then we just know it is arithmetic instruction, one of the arithmetic instructions, but we don't know exactly what instruction we are fetching, right? So because of this, we use four more bits to identify the arithmetic instructions in this category, right? So it is called function, and also same goes for jump instruction, right? So I code is 7, but there are many types of jump instructions. So to identify jump instructions, we use fn, function, okay? But the other instructions doesn't have to have this extra ID, because one instruction format has like corresponds to exactly one instruction, no more than one. So because we don't need, we just ignore, or we just write 0 and ignore this 4-bit when we decode instruction, right? Okay, good. Then this part is actually called ifun in the later figure. Okay, good. So these first two boxes, the first byte or first 4 bits are fixed, and it has its own meaning and same meaning for all the instructions. But later bytes has different meaning for different instruction. So because of that, let's see one instruction by one instruction, and then understand the meaning of later bytes. Okay. So since first two instructions, hold and no op, is done, so its size is 1 byte and it doesn't have more information. So we move to next instruction, RR move instruction. So it has 2 more small boxes, which is 1 byte, and it has RA, RB. So RA, RB, we are familiar with this. This is the name of registers. So when we use RR move instruction, we write RA, register in the RA position, and it is one of the operand. And RB is another register, and it will be used operand, and also result will be stored in this RB register. Okay. So when we read second byte, then we can get RA and RB in register. But since it is machine code, which is binary, so we don't write like EAX or EBX like register name. Instead, we use ID of each register, like 0, 1, something like that, right? So then, then there is a table of instruction ID. So you can refer to that table. Then when we read this byte, then you can understand which registers are used. Okay, good. Okay, then we understood RR move instruction, and let's move on to next instruction, IR move instruction. It is similar, but the first box has F, not RA, and second is same, RB. So actually, RI move instruction does not have RA, does not need RA. Instead, it needs immediate value. Okay, so immediate value is 4 byte long. So to make implementation simple, we don't want to we don't want to make this format very different with other instruction format. So we just leave the first box as blank and then put the immediate value in the last part here. So, but we should mention, okay, to the like machine code should indicate that you shouldn't read RA register, or you don't have to read RA register, right? Otherwise, maybe we do some mistake or some issue in the implementation. So to notice that, we write F, which is not register ID. So this is not used value for register ID. So then machine code can understand when it reads F in the first 4 bits in the second byte. Oh, okay, so it means I don't have to read RA register in this when we fetch this instruction. Okay, so F has that meaning. And when we read this, the Bryant book, this F is like used. I mean, it has a nickname like R none. But just you ignore this. As long as you understand meaning of S, then you can implement. Okay, we understood our I move instruction as well. And then next is our M move instruction. So in the first 2 bytes are same with RR move instruction, right? So instruction code, function ID, but not used, and then RA, RB, register IDs. But since it is a register to memory move instruction, to specify displacement in the memory, we need to use constant value, which is distance, displacement, right? So, but then we understood our M move instruction. Okay. The next is our MR move instruction, and its format is exactly same with RM move instruction, but we know the direction of data movement is the reverse way. Okay, and then OPL instruction, we just understand how to read this format, and also jump instruction. But jump instruction has destination, which is also, this is also constant value, but the meaning of this constant is the address of address to jump, right? The address of the instruction where we want to fetch in the next for the next instruction, right? But in this case, we have 2 cases. Like when I explain how PC is updated in the before, I wrote this way, PC plus len. But this is the common case. But when we fetch jump instruction, right, then we have 2 cases. Like first is take the branch, which means we jump to the destination, or we don't take the branch, which means we just fall through, or we just fetch the next instruction, right? So when we don't take the branch, then we just use this equation to update PC. But if we decide to jump to the destination, then we just update with destination and value in the instruction, right? So this decision making will be done during the execution, but in this week we are not going to implement execution unit, so we don't have this case. So even though we fetch jump instruction, we will just update PC with this equation. Okay. All right. Okay. Then we understood how to read this format. Okay. So then we can actually do encoding and decoding, vice versa. Okay, so then let's take an example and practice to decode this machine code. So let me write one example. This is a hexa number 30 F F0 and 46000000. Okay, first I'm going to decode as fetch unit does. Okay, so let's say this machine code is stored in the memory. So fetch unit will fetch this instruction, but before we fetch the instruction, we don't know how many bytes we have to fetch because each instruction has different size. But we know the maximum instruction size is 6 bytes. So we just, like unconditionally, we just fetch 6 bytes first. Okay, then let's say we just fetch this 6 bytes instruction machine code from the memory and then put into the special register inside the processor. And then we read one like one by one. Okay, and we know the first in the first byte there are instruction code and instruction function. So we first read first 4 bits, which is one hexa digit, by the way. So you should get familiar with hexa notation because all the time in the system courses we use hexa notation, and in this implementation you'll read and understand so many hexa numbers, right? So we read first 4 bit, which is 3. Then we can check. We can find it is IR move instruction. Okay, this is IR move instruction. So then, okay, we know, then we can follow this format. And then second 4 bit has no meaning. We just ignore this part. And then second 4 bit must be F, otherwise machine code is malformed, right? So, okay, we have F here. And then second 4 bit is the place of RB. And then we see 0 in the next 4 bit. So then, but we know, okay, this is a register ID. This is a place for RB. And then we know this ID 0 is EAX. So you can go to the y86 tutorial slides to see the register ID table. So this is EAX register ID. Okay, good. Then later 4 bytes are constant value, and actually it is immediate value. Okay, so how many we left? Actually, 1, 2, 3, 4 bytes exactly, right? So then this is the immediate value, or V. Okay, then we can write down the actual assembly code. So IR move L, and then second place is the immediate value. So 46000000. But this is not exact immediate value. This is incorrect value. Why? Because when we store the data, so constant value is the data, but it's in the machine code, is stored using little endian style, right? So which means lower, the least significant byte is stored in the lower address. So we need to convert this value with to the exact the immediate value, which is 00000046. So if you are not familiar with Little Endianness, you can go back to the previous lab or previous lecture, or you can Google it and then go back to this slide. Okay, so then we we finished this V part, which is immediate value, and then RB is the register, destination register, which is EAX. Okay, we are done. We actually decoded the machine code and then come up with assembly code. Great. So yeah, this is the how we encode and decode y86 instruction, and this background will be used to implement fetch and decoding unit. Okay. So you can practice with more machine code, and then once you understand how to encode, decode in machine code, then you can go to the next slide. Okay. Next, this is the now we can talk about fetch unit, and also we will talk about PC update stage briefly. So let's start with just basic idea of fetch unit, like what to do, what it does. Actually, fetch unit fetches one instruction from memory using PC register. So what is PC register? PC register is a special register to store the memory instruction address to fetch. Okay. And then here in the slide, it is written like we fetch 6 bytes to fetch one instruction, because we don't know how many fetch unit, how many bytes we need to read, exactly how many bytes we need to read for current instruction. But so to make our implementation simple, we just read 6 bytes and then read first 4 bit, then we know, okay, how many bytes we need to read, right? We can just ignore some later bytes if the current instruction has small size. Okay, next, once we fetch a single instruction, then this fetch unit produces a meaningful data and control signal from the fetched instruction for the later stages, like decoding stage. So you remember these names like iCode, iPhone, IR, RARB, VLC. Not so you don't know this yet, but so what we decoded in the previous slide is actually producing the information for decoding stage. Okay, this is done during the fetching the instruction in the fetch unit. Okay, then what is VLC here? It is actually constant values in the instruction format. So what are the constant values we have? So we had V, which is immediate value, and D, which is displacement used to calculate memory address, and then destination, which is the destination of the next instruction. Okay, done. And okay, so after we fetch a single instruction, we break a single instruction into small pieces like iCode, iPhone, RA, RB, blah, blah, blah. And then those small pieces with meaning will be used by next stage. And then next thing is last thing in the fetch unit is to calculate one of the candidates for the next PC value. Okay, so you remember we have two cases to update PC values, like PC plus length of current instruction, or we update with destination. Excuse me. So this value is actually one of the candidates. Actually, we may have more, but anyway, this PC plus length of instruction is one of the candidate, and it is calculated by fetch unit. Okay, and this PC plus length of instruction is called val p here. So you will see this variable name in the detailed hardware structure in the next slide. Okay, and then this like decision making, like which candidates should be used for the next instruction, will be done by PC update stage, which is the last stage of the one execution of a single instruction. But because we have only one candidate in this week, this PC update stage will be super simple. Okay, now we understood this yeah, the basic idea of fetch unit and PC update stage. Let's move to the next slide. Okay, this figure is 4.23 is, and you will play with it a lot in both lab and lecture. And this is the really important figure in the in your quiz as well. So you should practice, you should get familiar with it. But in this video, I'm going to give you just high level idea, how to read, what it means, something like that. But if you don't see, sorry, maybe it's not clearly visible in the video. So if you don't clearly see the names on this diagram, you can go to the Bryant book and then check this figure. This is figure 4.23. Okay, let's go ahead. So here you see some names on the left side: fetch, decode, execute, memory, PC. So here, this is the logical boundary of this whole hardware structure in with the role of the hardware component. So around this part is called fetch stage, and around this is called decoding stage, and around this is called execution stage, and this area is called memory stage, and then last part is called PC update stage. So so you feel like what they do basically, like fetch unit fetches instruction, decode unit decodes the fetched instruction, execution is executing instruction, memory is reading or writing data depending on the instruction, PC update stage is just update next PC, new PC. Okay, so then here let me highlight the components we are going to implement in this week. So we are going to implement this entire fetch unit. Here you see the output of this fetch unit, like iCode, iPhone, RA, RB, VelC, and VelP. We already know these outputs, right? So this kind of information is called data in this structure. And also we have some more information outputs, which is around here. So maybe it's hard to see, but we are not going to talk about it in this week, so just ignore it. But I just want to tell you that this is the control signal. So here you should recognize what is data and what is the control signal. So this is the control signal. Oops, sorry. So these two are control signal generated by fetch unit, and then it is actually using the dotted line to show the path, the flow of this signal. Okay, so this line is actually dotted line, but data line actually uses just line. Yeah. But you see some thin line and thick line here. So that the thin and thick lines represents how many bits are used for that data. Okay. So for example, VLC value, actually we know how the size of VLC, which is 4 bytes, has a thick line because it has a many bits. But I code is thin, so this is 4 byte, which is 32 bit, and I code just need 4 bits. So that's why it has different like thickness in the line. Okay. So in this week, we just produce the data, but we don't implement some next unit which uses this data, except val-p. Okay. So we need to implement this val-p along with this line. So I'm following the data path of val-p, and it goes to a PC update unit. Actually, it goes to the memory unit as well, but we don't care memory unit in this week. We just focus on the data path to the PC update unit here. And as you can see, there are many data going to the PC unit, and those are candidates of the next PC. But we don't implement this data line and this data line, but we only have this the right data line, which is val-p. So when you implement UPC module in this figure, you just directly connect val-p with output UPC, just like this. Okay, because we don't have to make a decision in this case, because there are only one candidate. Okay, good. So the highlighted part in this figure, we will implement in this week. Yeah, only this much. Okay, let's move to the next slide. And I think it is the last slide. So here we can discuss detailed implementation of fetch unit. And this is a little bit more detailed of fetch unit. And let me draw the borderline. So because we don't see exactly what is input, what is the output of fetch unit here. So let me draw this way. Okay, let me use a little bit thin line. Okay, sorry, it's too long. Okay. So, but it's up to you. It's up to your design. Okay, I would draw a line of fetch unit. This is the fetch unit. So when you implement fetch unit using the logicin, you can create a new circuit which is fetch, and then you can decide what is input and what is output here. So then let's take a look at what is input and output. So I'm going to use green for input. So actually input is 1, so PC. Okay, so fetch unit takes PC value, current PC value as a input. Okay, let me write here. Input is PC. Then here we should know how many bits we should use for PC register. Okay, so actually basically PC register stores the address, right? Address of the instruction we are going to fetch. Then we should know, okay, what is the address line size or address line width? So you can decide this the size of PC and also address line size. Okay, so recall that in the lab 4 problem 2, when we design and implement I/O system, we used 8-bit address lines and 8-bit data line. But think about how many bits we need to use for y86 instruction set architecture. Okay, I'll leave it just for you and you design yourself. And then next, I'll use blue color for indicate output of this fetch unit. Okay, here we have one output, I code, and another output, iFun, and next RA, next RB, and last, not last, val C. Okay, so we don't know where, in which unit it will use, but we just produce this output and we will use it the next week. And also, actually, we have few more outputs, this and this. And we see where it goes. Actually, it goes to the PC increment module. This is another module beside this fetch unit. And we have a small, what's that? Small, you can consider this register or any like just wire or just name of this like line or wire. It's up to your design. But this is 1-bit information. So in here, in the writing here, read VLC is 1-bit flag to indicate that the whether current instruction includes the constant value, VLC or not. So if the current instruction has constant value, then this flag will be set 1, right? And second, read reg IDs actually also a 1-bit flag to indicate that if the current instruction includes register IDs. So as long as it has at least one register ID, then this flag will be set. Okay, so then why we need and why it is used by PC increment module, and what is PC increment module? Okay, actually PC increment module calculates val p, right? Val p, which is one of the candidates of PC next PC value, and we know val p is PC plus length of current instruction. Okay, but to calculate the current instruction size, this module uses read VLC and read reg IDs. Okay, and then we name it I and R. Okay, so then PC increments also takes PC value as an input, right? And then use this equation. PC plus 1 plus R plus 4 times I. So it is actually a smart way of calculating PC, next one of the PC value. So here let's play with some examples. So for example, IR move L instruction, which is V and RB. This is the format of our IR move L instruction. Okay, so does it have the VLC or constant value? Yes, V is constant value, so we set I value. But what about the register? Oh, yeah, there is a register ID in this format. Okay, then we set R as well. Then PC value will be PC plus R 1 plus 1 plus 4 times 1, just 4. Then this is PC plus 6. Okay, 6 is the actually size of IR move instruction. Great. Then what about jump instruction? y86 destination. So it has a constant value, destination. So we set I, but it does not have register IDs. So we reset or put 0 here. So then the next PC will be PC plus 1 plus 1, 0, R is 0 plus 4. Then it is PC plus 5. Okay, it's correct because it actually the jump instruction, size of jump instruction is 5. So next PC is PC plus 5. Interesting. So in the PC increment module, you just implement this equation. Simple. So PC increment module is simple. But fetch unit is a little bit challenging. So here, but we just listed out input and output of fetch unit. So let's go back to fetch unit again. The input is PC register value, and then outputs are I code, iPhone, RA, RB, and VLC, and lead VLC and lead reg IDs on the right hand side. But we didn't talk about this part and this part and this part, which are all control signals, but we are not going to talk about this in this video, and maybe we will talk about it later. But then let's talk about how to implement inside this fetch unit. So let's recall what it does. Like there are 3 steps, right? And then actually last step, which is updating PC value, next PC value, exactly VLP is implemented in the PC increment. So we just focus on the first 2 steps. So first step was fetching the 6 bytes from the memory using the PC value. So because input is PC, so using this PC value, we can fetch 6 addresses. So for example, if PC is 0xa, then we fetch address, the data in 0xa, 0xb, c, d, and e, f, right? A, B, C, D, E, F, 6 bytes. Then here, as you can see, okay, there is a instruction memory in the fetch unit. Okay, I think I didn't mention about this instruction memory, but you just, okay, let me go back to the previous slide. Then clear this, and then I will restore this later. So in the fetch unit, it has instruction memory, and also there is another memory which is called data memory, and which, so here we can understand machine code is stored in the instruction memory, and the data is stored in another memory which is called data memory. So this structure uses two separate memory to store machine code and data separately. Okay, so why we do this? There are good and bads, but in our like some PC, some other type of PC or processor like Intel PC actually use different structure, and it is called, so this structure is called Harvard style architecture, and it stores machine code and data in different memory. Then it is easy to implement fetch and memory unit because they are not they are not related. Like they are not they don't have to communicate each other. Then there will be some simple control signals. Okay. And also there is another type which is called von Neumann style architecture. And this architecture uses a single memory, and it stores both machine code and data. And many common processor in these days uses von Neumann style. But in this y86 sequential processor, we use Harvard style because it is simpler to implement. Okay, so then you think about, when you follow this structure, then you think about how to make binary files. Then you should have two different binary files, one for machine and the other for the data. Okay, let's go back to the next slide. Then let me restore. Okay, this notation. Okay, good. Then we are back to the fetch unit, and we are talking about the first step, which fetching the 6 bytes from the memory. So then around here, you should implement some logic to generate the address and control signal to this instruction memory, and then it returns data, right? But so when you create a ROM or RAM for instruction memory, you can configure the address line size and data line size. But depending on the data size, you can have just different number of requests. So for example, so this is the RAM, and let's say this is the address, and this is the data. So here I don't care the address line, but the thing is, so if depending on how we configure this data bit size, data bit width, we can get the 6 bytes with one request or multiple requests. For example, if we use 8-bit data size, then we have to request memory to fetch 6 bytes using 6 different addresses, like here. So A, B, C, D, E. So like this. So please give me 8 bits at address A, and then we store it into the a certain register, and then ask again with next address B, and then ask again with C, D, E, F. Then when we ask once, then it will return 1 byte or 8 bits. But since we need 6 bytes, so we have to ask 6 times with different addresses. But if we use not 32, maybe just use 24, which is 6 bytes. Oh, sorry. Is it? So 6 times 8 is 48, right? So if we use 48 data size, then using just address 0xa in our example, it will return 6 bytes from like A, B, C, D, E, F address. Then it will be easy to implement, but you will see it's not possible in the logisim to have 48 bits. So at least you have to ask 2 times to fetch 6 bytes. So you will see that when you actually start implementation. So that will make you make this implementation a little bit complicated. So using your own control logic, you can ask to retrieve get the 6 bytes instruction, and then you put the first byte in the split. It can be register, or it can be register plus something else, something more like logic. And also next 5 bytes will be stored in a line. Again, it could be register, or it could be register with some extra logic, depending on your implementation. But either, also we have just large storage and store entire 6 bytes in that place. Okay, so this is just one example, so you can design your own way. And then from this storage, you just take 4-bit for the I code, another 4-bit for the iPhone, and next for RA, and next for RB and VLC. Okay, but the problem here, the challenging part is the VLC. Okay, let me clear this out and then talk about the difficulty of implementing VLC. Okay, so let's go back to the slide of this instruction format. Okay. So the VLC is basically constant value in the instruction format, like V, D, V is in immediate value, T is displacement, and destination is the address to go. But see, like for iCode, iPhone, register A, B are all fixed. So when we want to get RA, for example, we just fetch the first 4 bits in the second byte 1, for all the instructions. But when we want to take a val C, which is VD or destination, their start position is different. Like for V and D, it starts at byte 2, but destination starts at the byte 1. Okay, so maybe you should recognize, okay, I'm fetching jump instruction. Then to get val C, you can take destination from the byte 1. So then maybe you have two possible VLC, like VLC for V and D, and another VLC for destination. Okay, then using a mux, then maybe using this I code. Okay, depending this I code, so we will select upper VLC or lower VLC. Okay, you can use this mux to implement the logic to take VLC from the instruction. Okay, so I think this is the just most difficult or tricky part in what's that fetch unit implementation. And maybe last tricky part is timing or some timing of entire program. So what I'm saying is, once you implement a fetch unit, say we implement around this part and this part, okay, then we should connect this and all the necessary parts. Okay, then you will have a clock signal, clock generator, and then maybe fetch unit may need a clock signal, and also depending on your design, new PC module also may need clock signal, and then so you should see it works. It keep fetching the correct instruction. Okay, so maybe you don't understand what I'm saying, but in the next video, I'm going to demonstrate my own implementation, just with fetch unit, and then you will see what I'm saying here. Okay, I think we are done. Oops. Okay, sorry. So in the next video, I'm going to show you my implementation, and then you can refer to this for your implementation, and then please try to implement fetch unit within this week and then verify. Otherwise, it's hard to scale up your system. I mean, to build up your system. Okay, all right. Thank you for watching this video, and see you later.